Thank you for coming to Drinking from the Firehose. This is a talk about real-time metrics. It's a talk a little bit about what real-time metrics are and why they're important. And it's also mostly a talk about how we approach this particular problem at the company that I work for. The big reveal is coming. This is my Twitter handle, I eat killer bees. In case you don't know me, my name is Samantha Quiñones. You can reach me also on my website. I don't write as much as I probably should. Excuse me, I'm dealing with a stomach issue this morning, so if I'm, but if in case you, for some reason, can remember how to spell my name and can't remember I eat killer bees, you can actually get a link to my Twitter account from my website. It's the best way to get a hold of me. I work at AOL. Woo! So you might have heard the news recently. We got acquired by Verizon. When that news came out, who heard it and went, AOL still around? Stop it, Jake. No, we've been around for a while. We got spun back off of from AOL Time Warner back in 2009 and kind of became a media company. So that's where our focus has been. I've actually only been with AOL since October of last year. And I'll tell you a little bit of how that came to be. So I was sort of quietly in the market for a new job. And through a friend of a friend, someone at AOL reached out to me. And I was like, no, I don't want to work at AOL. I wasn't really interested. But it turns out this friend is actually a recruiter that I've known for a number of years. Actually helped me place some people when I was a hiring manager at another place. And sort of as a favor to him, I took the interview. And we had a really good conversation, actually, with the guy who's now my boss there at AOL. And it was enough to convince me to take a second follow-up interview with someone nameless in this room. It's that guy with the mohawk, who I just called Jake, so I guess he's not nameless. Anyway, so I took that second interview, and after that second interview, I was actually really interested in joining these people because they just seemed like they were interesting and knew what they were talking about. So I went to the real interview, the all-day, 8-hour marathon interview on site, and I met with a whole bunch of people. And I don't know if Shashi's here, but I'm going to pick him out if he is. He's not. There he is. He asked me a really interesting question when he was interviewing. He's also on my team. I'm not actually quoting him. This is a paraphrase. But how would you let editors test how well different headlines perform for the same piece of content? Right? So you have an article that you write, and you want to see if more people click on this headline or that headline. It's A/B testing, right? And this is actually, turns out, a kind of a hard problem at large scale. I love questions like this in engineering interviews because they don't rely on sort of trick knowledge or very specific technical information, but it's a great way to start a discussion about how an engineer approaches problems, design problems. So we'll come back to this question later, but just let it kind of percolate in the back of your head the way it percolated for me. What we're talking about here is measuring user behavior. And there's lots of ways that we can do this. You can measure the path that a user takes through an application, what they click on. You can look at their usage patterns. You can do mouse and attention tracking. So a couple of years ago, I think this was, I have the name written down in my notes, but I'll actually walk up here and look. Dreamscape Multimedia did a study, an eye tracking study, to kind of look at where people's attention falls on a web page. They call this kind of the F diagram. They kind of start at the top, move to the right a little bit, then scan down, and then after that top left corner, they kind of disappear. So you can do this by looking through eye tracking, but also if you can capture the position of a mouse, people have a tendency to sort of hover over what they're paying attention to. And then, of course, there's multivariate testing, which is what we were talking about in that question. In this case, what you're doing is you're taking taking your users and you're splitting them into test groups, right? You have a control group that receives the unaltered content, and then you have one or more treatment groups. I do have a sciences background. One or more treatment groups that receive the altered content. And then by using your behavioral statistics like click-through rate, abandon rate, scroll depth, all that kind of stuff that you're already tracking, you can kind of get an idea of which type of content, which text is performing to your expectations. We can also do production state monitoring, and we often talk about this in terms of live debugging, or kind of debugging, capturing exceptions live as they're happening in your production environment. But I think of this more as like state monitoring, and also load monitoring. So you can look at actually just how much traffic is flowing through the system, where it's bottlenecking, stuff like that, profiling. Going beyond those things, though, there's lots of awesome questions that we can ask. When you look at multivariate testing, A/B testing, that is a very primitive form of sort of augmented intelligence for content creators, right? So we're taking content creators, people who are already pretty smart and good at their job, and giving them the kind of tools that help them be smarter and better at their job. We can also think about doing things like quality prediction, looking at trends in content and how they perform to make guesses about how similar content will perform in the future, right? We can ask questions like, what if content could change itself based on the weather? And what I mean when I say that is, I wonder sometimes as I look at large flows of data, does the nation have a mood? Does that mood change from day to day? Are there days when America is happy? Are there days when France is sad? Can we capture that if it's true? And if we can capture it, can we use that to alter our content to fit the mood of the country? If the mood is in a somber, if the country's in a somber mood, maybe it's not the best time to write funny stories. So these are just questions that we're asking. You can also keep these in mind. But the problem for us at AOL is that we're working at a very, very massive scale. We're dealing with big data. And whenever you're dealing with big data, managing that data becomes a problem. I don't mean to stand right in front of the slides. Managing the data becomes a really big problem. And also the question, how big is big? This is a contentious question whenever you talk about big data, because if you have bigger data than somebody else's, you're like, my data is the biggest, and you have nothing. I kind of put when you're talking about data sets in the terabytes and up, kind of when Hadoop starts to make sense, we'll talk about Hadoop in a second, is kind of where we're talking about big. So for us at AOL, this is our magic number. 1.3 billion events happen in our system every day. Each of those events contains somewhere around 40 points of data. So that means we're averaging about 15,000 of these events every second. We can do a little bit, this is just arithmetic. We're talking about 600,000 data points every second. So it's a large amount of data. And it's moving very, very quickly. We're getting about 25 megabytes a second. It'll spike a little higher than that, but this is a good average. So when you're dealing with this level of data, you're kind of out of the realm of sort of typical approaches. And the way that we approach this, we have these collectors. These are front-end internet-facing collectors. They're called beacon servers. And we run code in our users' browsers, just JavaScript code that collects some information about state. And it's anonymous information. Like, please don't blog about how AOL is tracking your every move and thought. It sends it into a Rabbitmq farm. We'll talk about Rabbitmq in a minute, but we just basically collect all this data, throw it into Rabbitmq, and on the other side of Rabbitmq, we have Hadoop. So this data flows into Hadoop, and we just collect it and collect it. It's about 2 terabytes of data a day. So we just build up this data set constantly. Hadoop is really just is anyone not familiar with Hadoop? OK. I mean, Hadoop is somewhat poorly understood. It is really just a framework for managing distributed data. So storing data in a distributed fashion, and then managing and processing it in a distributed fashion. If you go back to the bad old days, if you were a company that was dealing with very, very large data sets, generally speaking, you were using very, very large, very expensive proprietary hardware and software to manage that data. Now, with Hadoop, we have really cool, well-documented open source software that does that same job on commodity hardware, right? So the fact that we can manage terabytes and petabytes of data on virtual servers in Amazon or Rackspace, or we have our own internal cloud at AOL, or just essentially on consumer hardware, really makes it economical to even store and think about processing data at this scale. Hadoop has a couple big pieces to it. The important part is the file system, the HDFS, Hadoop Distributed File System. It's based on the Google file system. And all it does is it takes files, turns them into sort of logical entities, and spreads them across multiple devices. It's cool because it's rack aware, so it's geographically sensitive. It'll store some data on a local server, put some data on remote servers. The big flaw that Hadoop has, if it has a flaw, is that I wouldn't say it's a flaw, it's just a fact of the matter. There's no read-write concurrency, so this is not a method that you want to use if you have data sets that you are altering. constantly. The idea here is you're going to take some data, you're going to put it into this storage, and you're really not going to change it at that point. What really makes Hadoop powerful, though, is this concept of MapReduce. Now, this is something that's probably a lot more familiar to everyone because we have implementations of map and reduce in our primary languages, PHP and JavaScript. Also, like in, you can do MapReduce in Mongo. Does anybody not know what MapReduce is? That's awesome. I'm going to go over it anyway. This is a really contrived example. We have a document that contains this phrase, I'm a little teapot, short and stout, here's my handle, here's my spout. We're going to take that document and we're going to look for instances of a target, and we're going to return an array that contains counters for each time we found that target word inside the document. Right? So we're going to look for the word is, and we're going to look through the source. Each time we see the word is, we're going to return a 1. Otherwise, we're not going to return a 1. We're going to return a 0. This produces an array that contains a bunch of counts. We can then take that array and use it as input to our reduce step. What reduce then does is just it iterates over a set of data, performs an operation, then takes the result of that operation and passes it into the next iteration. Right? In this case, we're just going to sum all of the data. So I'm going to start at 0 plus 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 1, yada, 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 yada. And we're going to end up with a 2. Right? So again, this is a really, really contrived example. The power here is that if you have a document that's not 10 words long, but a document that's 1,000,000 words long, you can break it up into 1,000 documents that are 1,000 words long, give it to 1,000 computers, let them all run that map in parallel, and then say, here's what I found in my part. Then you can take all of those findings, pass them back to those 1,000 computers, and say, OK, count up what you found. Take the sums from the 1,000 computers, put them together, and you have your final result. So we can operate on these huge, massive data sets. Instead of starting at the very beginning of a 1 terabyte file and reading through byte by byte, we can push that process out to a bunch of parallel processors. There are some limitations. A lot of them come from the fact that there is a point where it's no longer economical to throw servers at a problem. I think we all know that. So we have to batch these jobs up. Over large data sets, when you're talking about petabytes of data, it doesn't really matter if you're doing it on 500 or 1,000 servers. It's still going to take a little bit of time. So data might not be available for an hour or two. And if we go back to our original question, which was, how do we let editors test how well different headlines perform for the same piece of content? There's a big consideration here for our customers, who are those actual content creators. The shelf life of a piece of content that we produce for one of our brands is not very long. Most of the articles are relevant for less than 24 hours. A lot of articles are relevant for less than a few hours, right? So they're not interested in seeing how something performed yesterday or last week or last month. And in fact, when we talk to them about these problems, they're like, we really don't care what happened yesterday. Like, it's just not of interest to them. We need to know now. They have some interest when they want to roll up reports and look at more generalized trends over the past, once a month or once a quarter. But generally speaking, they're only interested in the last day or so. What they want is real-time information. They want information that's updating constantly and immediately. So they need a real-time pipeline. And this is kind of where my story and AOL's story come together. I'm going to define a couple of terms here because I tried to do a better job in this presentation than we actually do in our day-to-day job of keeping the terms collector, receiver, and streamer straight. So these are the collectors. This is the forward-facing stuff that's actually collecting information from, end users. It flows into a Rabbitmq farm. If you remember that original diagram, it kind of goes off into Hadoop from here. But now we also make it available as an HTTP stream. So you connect to one of these HTTP servers, and it just starts vomiting data at you as fast as you can take it. This is what we call the Firehose. It's shocking the first time you connect to it and look at it. You don't realize how difficult it is to deal with data at 20 or 30 megabytes a second. in a meaningful way. I mean, obviously we have hardware that deals with much, much higher throughput than that, but when you're actually trying to run application logic against data at that rate, it's pretty difficult. So my first day at AOL, actually my boss and I had like several conversations between my actually accepting their offer and my start date. So we kind of knew what I'd be working on when I joined the company. My first day, there were 2 things waiting for me. Obviously there was my AOL CD so I could connect to the network. And there was the Git repo where we had the very, very raw first prototype of a receiver that would connect to those streamers and pull the data. And I expanded that over the course of about a week and a half into version 1. So we have here the streamer. This is the part that's vomiting up all of that data over it's an HTTP streaming API. We have a receiver. This is a piece of code that's connecting to that stream API, pulling that data, and then processing it. And then I stood up a statsd cluster, right? So has anybody used statsd? OK. Statsd is a really cool tool. I won't get into too much depth because it's not important to the story, but it basically takes in data, aggregates it in memory, and then sends it someplace. In this case, I had it sending it to Elasticsearch. So it took me about a week. Actually, I forgot I had this slide. This is sort of what that application ended up looking like. So I did this in Node. I primarily work in Node these days because I'm a bit of a hipster. Node, if you're not familiar, though, has a really, really powerful streaming component. So it's very, very easy to work with data in streams. So I connect to that HTTP streaming client. I create a stream out of it. It's a line delimited stream of data, so I break it up into chunks. I create an event for each chunk of data. It goes onto Node's sort of logical message bus into the event loop. These little visitor guys, they see that event, they respond to it, they make some edits, produce some statsd information, and send that out to statsd. There's one piece of this architecture that has survived to this day, and it's these little guys on the right. We wanted these to be nice and modular. And we did a really good job because this code is largely unchanged from version 1. Essentially, to pull out the user agent from a record, this is it. This is all the code that does it. Obviously, we're using a third-party user agent parsing library. But essentially, those little processing steps are decoupled from the rest of the application. And because we were using statsd, we got a really cool add-on benefit is that it worked with Kibana. So I took this screenshot on my 8th day at AOL. And the proof of concept, I mean, worked, right? I mean, we were able to see sort of in real time the countries like get lighter and darker based on where the traffic is, right? So this is the first time we were able to prove that we could take this data in real time and do something marginally useful with it. It was way too slow to be useful, though. We were at 300 events a second. Remember, we need to get to 15,000. We would have needed 70 servers running receivers to make this work, which was not something that was going to happen. And statsd had a little bit of an issue for me where it took that data and it broke it apart. It severed the connections between pieces of data. So instead of knowing that someone at a particular geographic location looked at a particular piece of content on a particular device, we knew that there was somebody that looked at something from a particular location, and there was somebody that used this particular device, but we have no connection between that information. So that was a bit of a problem. Version 1 was not going to be the solution. And it was around this time that I started thinking about what kind of constraints I could add to this application to make it a little bit more performant and maybe a little bit more easy to comprehend mentally. I came up with this idea of transits and terminals. So transits are essentially short-term, in-memory, volatile storage spaces. They have a lifespan of up to a few seconds. And this is kind of where data lives while it's moving from point A to point B. Terminals, on the other hand, are where data goes to either die, we delete it, drop it on the floor, send it into another transit, or store it somewhere. And I kind of set a little goal for myself with this application, because I kind of believe that to have an efficient real-time data pathway, you need to have a network of transits and terminals where really you don't have any single node acting in both capacities at the same time. right? So this is not any kind of hard and fast rule. This was a rule that I created to guide the evolution of this architecture. StatsD, in addition to breaking up all of my data and making it impossible to do like cross-point aggregations, violated that rule, right? So because it acts as a transit, it takes data and passes it along, but it's also doing this in-memory aggregation kind of stuff. So it's also acting as a terminal. So that was kind of the last nail in the coffin for StatsD. We kicked it to the curb. So StatsD went away, and now we have Rabbitmq. So we have our receiver. It's pulling in data from the streamer. It's dumping it onto Rabbitmq, and then Elasticsearch is actually consuming it directly from Rabbitmq through the Elasticsearch river. Elasticsearch has this really cool add-on that basically lets it connect to an AMQP instance and just suck all of the data out of a queue. I like code that I don't have to write. So this was version 2 of the receiver. It looks very, very similar, but there is a very important distinction here. Node is very, very fast. If you're not familiar with Node directly, maybe if you're familiar with React PHP, it is similarly very, very fast. They both work in essentially the same way. They're using an asynchronous event loop in a single thread. It's fast in almost all cases. Turns out this is a case, this just very, very high throughput is a case where it's not too great. So I actually got rid of the eventing. So I created a clustered node process. So in this case, I'm running a copy of this node process per core in the system. And as data flows in, we generate the raw record. It runs sequentially through a chain of processors that create an enriched record. And then that gets pushed out to Rabbitmq. Rabbitmq, is anybody not familiar with Rabbitmq? OK. Rabbitmq is essentially a message broker. It's very, very lightweight. It's a piece of software that runs on a system. It can cluster together, so you can have multiple computers working together. And essentially, it just moves data from one place to another. And it gets a lot of use in this architecture because of my transit concept. It's basically the prototypal transit. So if you put data in and you basically tag it and say, this is X kind of data, something can sit on the other end and say, give me all the X kind of data. And it handles all that sort of routing logic, again, without me having to write code. My favorite code is the code that I don't have to write and maintain. I did not plug my laptop in. We're going to be out of juice. The other big thing that Rabbitmq gave me is that it can buffer for about 120 seconds. What I mean by buffer is if we start pushing data into Rabbitmq without consuming it back out, we have about 2 minutes before Rabbitmq just falls over, just from being overwhelmed with data. And that doesn't sound like a lot of time, but just having that 2 minutes of breathing room means a lot when you have a little bit of a hiccup or maybe a big spike of data come through. If it takes 10 or 15 seconds to clear that backlog and catch back up, we know we're not going to lose data. So we were able to not just have it be fire and forget, right? So this was important for us. Version 2, like I said, we eliminated eventing, got some better performance, got rid of StatsD, replaced it with Rabbitmq. All of our records are kept together, which is nice. Unfortunately, that nice, like, out-of-the-box integration with Kibana with the maps was kaput. Version 2 had another big problem. Now, early in my career, get ready for it. Early in my career, I did year 2000 remediation. So I was working on fixing COBOL programs that had been written in the 70s that didn't deal with date calculation very well. This is relevant to someone in the back of the room. And it was really common in this very old code to do goofy things like overflow a register, and now you know you have a -1 in this register. So later on, when you need to decrement a number, instead of decrementing that number, you just add that data from that register. It's a -1, so it works. And now something goofy happens, and some positive number gets stuffed into that register, and your math is off, and you have a bug, and you have 9 million lines of uncommented COBOL source code. And then you're either the kind of person who enjoys a challenge like that, or you're a person that quits and gets a real estate license. Very well, thank you. So I was actually starting to do real like micro-optimization of this code. And I was doing things like looking at different methods of pulling the first element of an array off and looking at like which one performed better, which is really interesting, like fun for me as a programmer, but is an indication that I'm writing brittle code that's going to break a lot and make people hate me. And I don't like people to hate me. So in the end, we doubled throughput to 600 messages a second. And that would mean we got our number of receiver servers down to 35, which is good. But I was really concerned that this micro-optimized code was going to be really, really bad for the future. So we had to revisit the architecture again. I had to get serious this time. So I needed something that was very, very high throughput, something that was would let me have like a multi-threaded worker pool, something that would let me do some static and dynamic optimization. I'm dealing with a large amount of volatile memory, so I need to be able to manage memory efficiently. And I wanted to get rid of that last bit of processing overhead at the receiver layer. I want the receiver to be a pure transit. Some other requirements: no Go, because no one on the team knows Go. No Rust, because no one on the team wants to know Rust. And no C, because I ain't doing it in C. Just go. Now, when I first started this project and I was having initial conversations with the people that had set up those streamers, they told me, you're going to want to do this in Java. And I said, it's 2015. I am not doing this in Java. I'm going to do it in Node, right? Node is web scale. It's going to be fine. It was a hard day when I had to admit I was wrong. Turns out Java was really the answer for us. What's cool about Java? You'll find out on my next slide. I don't know. This is pointless. Java has a really good suite of tools, solid like static and dynamic analysis tools that are kind of built into the source to bytecode compiler, into the JIT compiler. There are open source clients in Java for basically anything that you need to do. Certainly all the things that I needed to do. And AOL is pretty well supported, both in AOL in general, and also there's a couple people in my team, Shashi, who basically knows everything, can pick this up. So we've been talking at this conference a lot about bus factor. You want to keep your bus factor as low as you can, right? So this lowered my bus factor. And I think Java, honestly, I know everybody laughs about Java and we make fun of it. Java gets a bad rap for the exact same reason that PHP gets a bad rap. It's because shitty people write shitty code, which you can do in any language. Java's not that bad. Give it a try sometime. You might like it. Version 3 ended up looking like this. Right, so the receiver has completely been rewritten in Java. Rabbitmq is the same. Because again, code I don't have to write, yay! And this is basically like the leftover pieces, like the pulling apart the messages, doing the user agent parsing, that kind of code has kind of been pushed off into its own set of services. They can kind of sit over here, and it's fine. They don't have to keep up with the stream because they have that little bit of a buffer in front of them. So they don't have to be quite as performant. It ended up looking like this. We stream the data in. Again, it's still just a line stream, so we're breaking it on lines. And then we have a work queue. So we just round robin through all these worker threads and say, here's a piece of data, here's a piece of data, here's a piece of data, here's a piece of data. And the only thing that they do is take that piece of data and send it to Rabbitmq. They're not doing any kind of, there's no logic there. The code itself, which I'm not going to go through, unless you really want to read this, is actually quite simple. I mean, all it's doing is it's bootstrapping a bunch of threads, creating some essentially linked lists. And every time we get a record, it's sending it to Rabbitmq. This is the kind of the code that's being executed by those worker threads. So it's fairly simple. I call this my ketchup bottle map, or my ketchup bottle diagram. Essentially what it looks like, you have network input. It goes into just a bunch of little queues, like little baby queues, and then comes out the other end, as data does. So this is a pretty simple piece of code, even though it's written in Java. It's a lot simpler than the Node stuff. I knew that this was going to be more performant. I didn't realize that it was going to be more than 4 times more performant. Each one of these processes, and again, they each have multiple threads running, but each one of these processes can handle about 2,600 events a second. which means that to pull the entire production feed, we need 10 servers. That made my boss happy. So there's been this big bubble on a lot of these diagrams, Elasticsearch. And I don't think a lot of people think of Elasticsearch when they think about kind of big data. I love Elasticsearch. And again, I want to make one thing clear. We're not replicating what we do with Hadoop in Elasticsearch. I keep 3 days of data in Elasticsearch, so like 6 terabytes. It's not like a huge amount of data that I'm storing. Elasticsearch is a search engine, a Lucene-based search engine. Essentially, it can also act as a very highly distributed storage engine. It clusters really, really nicely. But the killer feature is this nice suite of built-in aggregations that you just get out of the box. Stuff like geographic boxing and radius grouping, right? How many things happened in this square on the Earth? How many things happened within a mile of this point on the Earth? Can do time series aggregations, histograms, standard statistical, like min, max, median, average, standard deviation stuff. I say MapReduce coming soon. This is in 1.5, so it's been released. So you can do MapReduce now if you're running the latest version of ES. Elasticsearch lets us answer really cool questions, like how many users looked at this post on an Android tablet within 10 miles of Denton, Texas? It lets us say, what's the average time from the start of page load to the first click for readers on Linux desktops between 3 a.m. and 5 a.m. And as someone who's in media, that's the money demo. Or the first question, rephrased, given 2 sets of link text, which has the higher click-through rate? For some sample of users, right? Multivariate testing, A/B testing. It's very, very simple. Even more importantly, this architecture lets us go browser to browser in less than 5 seconds. When I say browser to browser, what I mean is that user in Denton, Texas, clicks on an article in Engadget, and less than 5 seconds later, an editor at Engadget can see that happened, right? Obviously, they're not interested in that particular click, but the statistical the statistics shift immediately. So, right, end of talk, like, did it. Awesome. So we did this, and my boss was happy, but he's like, well, it's not really real time. And my boss loves saying, I had this great picture that I had been saving for ages to use in this presentation of my boss breakdancing. So I just want you to picture it in your head. You found it? Oh, you're killing me, Smalls. But my boss is a really brilliant guy, and he annoys the shit out of me sometimes when he's like, yeah, but it needs to be native real time. I'm like, what is native real time? What does that even mean? It took me a while, but I finally figured out what he was talking about. What he was talking about is doing live analysis of data as it's collected. And I think I rejected this because from an objective standpoint, it's kind of pointless. But looking at these kind of short-term trends in data, what he's looking at is creating visualizations that are kinetic. Why does he want kinetic visualizations? A lot of people who are not particularly technical have a somewhat animistic view of technology, in my experience. And I don't say that as a negative way. I think that's how, as humans, we've just kind of evolved to approach things that we're unfamiliar with in the world. Their whole life is centered around producing this content, and it just kind of goes out into the ether, and people consume it. They know people consume it because people click on ads and they make money. We're not all starving to death. But being able to kind of see a system that looks alive to them lets them create an emotional connection to what's going on. So there are some big problems when you're talking about trying to do live visualization of real-time data. When you're looking at data, sample size is really important. And when you're looking at the last 500 milliseconds of something happening, it tells you nothing about trends. Like any given half a second can look very different from every other given half a second. In addition to that, the data volumes we're talking about are too high for a human mind to comprehend. And even if you were like a super genius, or maybe Shashi, and you could comprehend 25 megabytes of data every second, your browser isn't going to do it. When I first started working on this project, I can't tell you how many times I crashed Chrome. It just explodes. So this was a new problem, and it's kind of interesting. It's less interesting to me, I think, because, like I said, it's kind of pointless. But we added in this new piece over here. Actually, this arrow should kind of come from Rabbitmq, but we added a WebSocket server. Right? So WebSockets are really cool. There was a great talk here about WebSockets. Who went to the talk about WebSockets? Yeah. So version 4, we added a WebSocket server. It just jumped. And it looks like this. It's really, really simple. I'm using Socket.io, which is a really cool library that's available in JavaScript. I like doing this stuff in JavaScript. First of all, hipster. Second of all, it's kind of nice because the same library works both client-side and server-side. It's really, really nice. We need like a PHP engine that runs in the browser. Wouldn't that be awesome? Oh, boo! So this is just an Express.js server, and one thing that we do is we consume this data as it's coming in, and almost every piece of data that comes in we just ignore, right? Because we have to downsample tremendously to make this even viable in a browser, right? So we just throw away almost everything at random. And then that gets pushed out onto the Socket.io event bus, and if there's a client connected and subscribing to a particular event, it will get that data, and it can do stuff with that. And to do stuff with that data, I use D3. Is anybody familiar with D3? OK. D3 is a really, really cool library in JavaScript for visualizing data. It's like modifying documents. Essentially, it lets you use JavaScript to paint on a canvas. People get scared of it, but it's just JavaScript. I mean, it's not that bad. It gets a little annoying because you do need to know some math. I have a helper for you. But what it lets us do is take a look at this live stream of data that's pouring into the system and do this. Now, this is a map of the English-speaking population on planet Earth. We are almost universally like an Anglophone company. I look at this and I go, OK. That's where people who speak English live. But I'm not looking at it from the perspective of an editor who sees kind of this technology as a black box. What they're seeing is, wow, that's people reading my stories. That's people that are engaging with my brand. They're a marketer. They say things like that. So this is kind of cool. We can do some things to try and make this a little bit more meaningful. Instead of having those kind of like pulsing dots, I tried color coding them based on what the person was looking at. And here you see some interesting trends. So you see a lot of activity, the little green dots. That's dailyfinance.com, which is a blog that we own that covers like the stock market, stuff like that kind of stuff. In the financial centers, so New York, London, Paris, right? Places where you expect people to be consuming that content. Autoblog is really big in the US Midwest, the South. For some reason in Russia, a lot of traffic in Russia for cars. Right, so you can start to sort of mine some interesting data out of here. Again, it's still a map of English speakers, but what are you going to do? One thing I love about D3 is that it lets us go back to high school geometry a little bit. Right, so if you ever, just bookmark the slides to this talk. If you ever need to calculate the location, the point of the vertices of a regular polygon, given the center point of the polygon and its radius, I got you back, baby. I got you back. Woo! In addition to doing mapping, though, D3 lets us do things like sort of linear analysis, right? Just looking at activity in unique ways. And I call this the heartbeat monitor. I call it this because it kind of looks a little bit, it's kind of faint on this screen. It kind of looks like a heartbeat monitor in a hospital a little bit, if you don't think too hard. One thing that's important to notice, this is completely divorced from quantity. Now again, this is reading a tiny sample of the actual data that's coming through the system. So if I were to put numbers on this axis, people would be like, why is my traffic so low, right? I could multiply it by the same factor that I'm reducing it, to kind of approximate what they're looking at. But they don't really care. I mean, they can just see that stuff is happening. And stuff like this, which is actually not meaningful, this is like a place where the system lagged for a fraction of a second, and we had a paint cycle happen. It just happened to be that we didn't put any new data in during that paint cycle. So you get these little dips and jumps, and people look at this and say, wow, that's really cool. But we can also use it to do, this is not done with E3, but you can also use this sort of real-time data to do things that actually are useful. So we can create a story, and Shashi's probably going to throw up when he reads this, but we can create a bunch of different headlines for a story and see which one does better. Right? How many people saw it? How many people clicked on it? What's the percentage? You can make these boxes turn green when it's a good percentage. Something that's really exciting for me, so the first time I ever gave this talk, I had an item on my to-do list, like things that we're going to do next in the future. Now it's not on my to-do list, it's on my to-did list. We can tag put a tracer on a person's browser who works for us, not, again, please don't blog about how AOL is tracking your every thought and move. We can use this for debugging. So we can put a tracer on somebody's browser, and then when they interact with content, we can look at all of the things that are executing inside the render farm, right? This is a hard thing for us to do. We have hundreds and hundreds of servers out there rendering content. We can't just sit there and tail the logs. It's insanity, right? And if you're using something like Logstash or Splunk, we use Logstash because we're a little bit cheap, but if you're using something like Logstash, you still have this the data comes in and it gets indexed, and after maybe a half a minute or 2 minutes, you can go search for it and try and figure out what's going on. In this case, you just have the screen up over here, have the content up in the other screen, and refresh the page, and you can see what's happening. These are, I'm trying to get my coworker, Ralph, to give a talk at Tech next year about what this is. This is one little line where it says API posts.query. This would blow your goddamn minds. I'm not even joking. We can actually look and see how long each of these pieces took as a component of the total request. We can look and see the actual context of the request that was running. In the new version, this is a capture from a little while ago. In the new version, we get information about the memory state that was going on inside of that system, right? This is useful for our developers, because as much as we have customers that are content creators, we also have customers that are actually developing sites. I don't create the Engadget website. That's another set of developers. I don't know who those people are, but they're building it on our platform, right? In the end, what we came up with is a pretty cool architecture, in my opinion. I can say that because I came up with it, where we have these layers that are geographically decoupled. They're all capable of being independently scaled, which is generally a good thing. And there aren't any cross-layer dependencies between them, right? So we end up being able to have the kind of applications that I love, where each piece is engineered specifically for its own little task. We have our input streaming in Java, do all of our routing and filtering in Node. All the aggregation and stuff is in PHP. It's PHP running, the Elasticsearch API, but it's PHP. We're using D3.js, which I kind of almost consider its own language, to do our visualization. The multivariate testing is all written in PHP by Shashi. There's a lot of stuff going on, right? This is cool. This is fun to work on, right? When you're not stuck in one little rut all the time. So that leaves us to where we are right now. So it's May of 2015. It took us about 6 months to get to this point. We have our entry points pretty well defined. We have user data collectors. We have application code that's generating information for us. And what's really exciting about this is that was the easy part. That was going to be more dramatic, but my batteries are dying. What's next? Scratch the first one off, we did it. Being able to embed those visualizations, making them widgets that can be plugged into the software that our customers create. One that's coming very, very soon is on-demand stream filtering. So we have, instead of having to consume that entire Firehose, being able to create filters in that Firehose on demand. Say, I only want data if it looks like this. And something I talked about a little bit before, doing predictive performance analysis. Looking at a piece of content as it's being written and making an intelligent decision about whether or not it's going to perform to whatever standards the brand has set for that, whether that's to make a lot of ad revenue or to get a lot of social exposure. And even beyond that, when we talk about getting social exposure, doing real-time sentiment analysis. We have some really, really smart people on our team, and all they do is machine learning, sentiment analysis, stuff like that. Can they look at social sharing and be able to tell our editors using this platform, yeah, you're getting a lot of shares, but it's not because people liked your content. They're kind of making fun of it, right? Hopefully, I don't know, maybe next year, I can come back and tell you about it. This is me. I'm Samantha. Reach out to me at I8KillerBees. Please leave feedback for this talk and all of the other sessions that you've attended at Tech. It's really, really important to us as speakers to get that feedback. We do care. It hurts us if you're too mean, but be honest. We do try to get better. So thank you very much for your time. If anybody has any questions, we have a little bit of time left, so I'm happy to talk about architecture or stuff that you're trying to do or interested in doing.
You mentioned that you had that buffer in Rabbitmq.
Yeah.
And you said that it just falls over when that buffer fills up. Not just drop the events out, or does it just crash itself?
No, it drops the events. It actually stops accepting new events.
Oh, it stops accepting?
Yeah.
Okay.
Yeah.
Is there any way to tell it to just drop?
You can. You can. The thing is that we don't actually want to lose any events. This was an argument that I had a lot with my boss. In my opinion, like when you're talking about 1.3 billion events, if you lose a couple 100,000 of them, it doesn't really have a big impact. But it's his opinion that we should capture everything. So I put an emphasis on not losing data for good or bad. It's something that I was willing to compromise on, so it is what it is. Just leave me hanging, guys.
I did my part.
Thank you. Let's hear it for Tony Shark, guys.
Almost.